let us look at this example. We have a region R, which is the region of integration, and we'd like to evaluate this double integral. So according to the instruction, R is the region lying between the circle of radius 1, because x squared plus y squared equal to 1 is the circle of radius 1, and the circle of radius root 5. Okay, why root 5? Because I know the general equation is x squared plus y squared equal to r squared. R is the radius. Okay, so looking at the second equation, x squared plus y squared equal to 5, I know 5 is the square of root 5. So the second circle's radius root 5. All right, so this is the region R, okay? And from Fubini's theorem, we know that, oh, if I can write R in terms of inequalities of x and y, then I can evaluate this double integral using iterated integral. But if you look at this annual region, you realize it's kind of hard to use inequalities of x and y to describe this annual region. However, if I use polar coordinates, you will see that I'm counting for any angle, I'm counting any points so that the radius r is between 1 and root 5, right? So I would have radius r greater than or equal to 1, less than or equal to root 5, okay? And this is true for all directions. So for example, this direction is theta equal to 0, and we take the parts where r is between 1 and root 5. For another direction, we also take the part where r is between 1 and root 5, right? And this is true around the entire circle. So theta would be anything between 0 and 2 pi. So this describes the region R, okay? So now we realize that, oh, now this R can be described very easily, theta from 0 to 2 pi, R from 1 to root 5, okay? Then dA is being converted to R dr d theta, okay? And you have to pay attention. We have dr first, so the first pair of limits should be the limits for R, and the second pair of limits should be limits for theta, okay? The order is important. Now, what is x squared in terms of r and theta? According to the formula, x is equal to r cosine theta whole thing squared. So it's like that, okay? So this is the x squared under r and theta, and this is the dA under r and theta, and this is the limits for the region R under the polar coordinates, okay? So now, simplify what we have in the integrand. I have r squared times r, so that's r cubed, cosine squared theta, and dr d theta. So this, to r, the cosine theta is a constant. Ignore that for the second. Find the antiderivative of r cubed. So this is 1 over 4 r to the power 4 with lower bound 1 and upper bound root 5. Okay, so let me actually compute this by on the side. So this is root 5 to the power 4 minus 1 to the power 4. So this becomes a constant, and I evaluate cosine squared theta, integrate cosine squared theta from 0 to 2 pi. Okay, so let me continue here. So this is 25 minus 1 over 4, and cosine squared is equal to 1 plus cosine 2 theta over 2 d theta. Okay, so now what do I have? This is 24 divided by 4, so this is 6, and over 2, so divided by over 2. Right? So now this is 3. So now I have 3 times antiderivative 1 is theta. Antiderivative of cosine theta is 1 over 2 sine of 2 theta. And theta from 0 to 2 pi. Okay? So evaluate this. I get 6 pi as my final answer. Okay, so I skip a step because I don't have enough space, but you do what you need to do to finish the evaluation. What I get is 6 pi.